So if we go back to looking at exponential decay has a parent function that's modeled like this. And so if we took the line y equals x, and again that's the line from which an inverse is reflected. So the inverse of a graph is going to be reflected across the line y equals x. Okay, and so what we can see right here is where this would be. So once again, we have this point 0, 1. When we find its inverse, we switch the x's and y's, so it becomes 1, 0. So it's still going to have 1, 0 as its intercept. Okay, but this point right, or this portion of the graph right here, as it approaches this x-axis, is going to get flipped over, and it's going to start here, and it's going to approach the asymptote in the upward direction. This upper portion of the original decay model is going to be reflected across here, and it also is going to wind up coming down, passing through that given point. And so this right here, or when you're looking at these functions, this is the function for decay, a times b to the power of x, when b is less than 1. The absolute value of b is less than 1, so you're dealing with a fraction between 0 and 1. And this corresponding log function is going to be some multiplier a times the log base b of x. Again, when b has that same properties where its absolute value is less than 1. Right, so just like what we saw in the last, we have no horizontal asymptotes for this log function. We have a vertical asymptote at x equals 0. So again, we switch from that horizontal asymptote to the vertical as we switch the x's and y's. Okay, and just like with the last one, this is in fact going to be the horizontal shift. So if there is any horizontal shifting that takes place, the vertical asymptote will be adjusted. The domain and range, again, the domain goes from that horizontal shift to infinity. The horizontal shift will affect the domain as well. The range is all real numbers. There's no restrictions on the y's for this function. And then when you look at the left and right behavior of this graph, once again, the left, just like with the inverse of growth model, the left approaches the asymptote, but it approaches it up to the asymptote. And then the right goes down, or it falls to the right. And so those would be the general properties for the log function with the base that's less than 1. And so it's a fraction between 0 and 1 for that. All right. So we have one last example. All of the rules that we just saw apply to this, except now the parent function looks like this red graph. Okay? But I want you to see, just take a few minutes and see, can you identify the graph of the following function, please? Right. Even if you're not done, I'm going to go ahead and start talking through here. So the first thing you recognize, you're dealing with a log, and you need to understand there's two different ways to approach it depending on what the base of that log is. Is it a number greater than 1 or less than 1? So because this base is less than 1, the original parent function is going to be based off of this graph. So here's our parent function. And then we can go in and answer the questions based on the transformation. So is there any vertical shifting happening? It's going down 1. Horizontally, it's shifting. What value of x gives you a 0 inside here? 2. so it's shifting to the right 2. There is no horizontal asymptote for log, okay, but there is a vertical asymptote, and the vertical asymptote is x equals whatever that horizontal shift was. So again, whatever x is equal to whatever value of x would give you a 0 inside there, so 2. So I can move this over 2. So here is my vertical asymptote. Okay. Now if I go down to my x-intercept, it'll allow me to complete my sketch. So my x-intercept is solved by plugging in a 0 for y, and then just solving the resulting equation. Okay, so I type in, or I substitute in a 0 for the y. I now isolate my log, so I am going to add 1 to both sides here. I get 1 is equal to log base 1/2 of x minus 2. Once my log is isolated, I can then rewrite it as an exponent. So I take my base of 1/2 to the power of 1, set it equal to x minus 2. So all I need to do is add 2 to both sides. Well, adding 2 is like adding how many halves? 2 is 4 halves. So 4 halves plus 1/2 gives me 5 halves. So my x-intercept is going to be 5 halves 0. So if this is 3, okay, my 5 halves 2.5 is my intercept. And so now as I sketch this, it's going to have the basic form of that parent function. This is my graph. So I can identify my left and right behaviors. To the left, my graph goes up to the asymptote. To the right, it goes down, or it falls to the right. My domain extends from, again, it's my shifting or my vertical asymptote, so it extends from 2 to infinity, doesn't touch either one. My range, which is my y's, goes from negative infinity to positive infinity, again, all real numbers. And so there are the remaining pieces of information or properties and tendencies that exist for this graph. Right, we could type this in our calculator to confirm. If I go to my Y editor, I'll replace what I have. I'll hit green diamond 7, types in log. I write my expression first, x minus 2, comma, followed by the base, 1 divided by 2. Oops. So hold on. So when I type that in, I get x minus 2 first, comma, followed by my base, which is 1 divided by 2. Close off the log, and then the minus 1 transformation happens outside. And when I hit enter, I can see it confirms that I have it entered the right way. If I wanted to check my x-intercept, I go to the home screen. It's still set up in that function notation to solve for the x-intercepts. y1 of x is equal to 0, solve for the x's, and it confirms that 5 halves is correct. I can also take a look at the graph and should see that it's similar to what I have hand sketched. And what you see is you'll have a vertical asymptote at 2, and again it continues up infinitely there, and then up and to the left toward the asymptote, down and to the right, confirms the other behavior of this graph.